Welcome back. This is part 2 of chapter 3 or module 3. And we're going to talk about measures of variation. And we're going to start with the range. And the range is the max minus the min. So if we use this example here, that means I'm going to take the largest number, that's 26. And subtract the smallest, which is 22. So the range in this case is 4. And it'll be the same for this set as well, because the largest is 26 and 22 is the next one down. We don't use the range that much. However, we do use the standard deviation a lot. Standard deviation is a set of sample values denoted by, and I make my S's with a little tick down there, is a measure of how much data values deviate away from the mean. So picture, I have, let's say the mean is right here. And then I have some data here and here and here and here and here and here and here. What I want to know is what is the average distance from the mean that each of these data points are. That's what standard deviation is. And we have a formula, which we will not use. This is the summation of each data point minus the mean, sample mean, squared over n minus 1. However, we have machines that will do this for us. So let's talk about some properties of the standard deviation. Standard deviation is a measure of how much values deviate away from the mean. The value of the standard deviation S is always positive. And you can see that by nature of the formula, because the result of a square root is always positive. The units of the standard deviation S are the same as the units on the original data values. And what we mean by that is, let's say that we're talking about the mean height. And so we take everybody's height in inches. And if we find the standard deviation, that unit will also be in inches. The sample standard deviation S is a biased estimator. Of the population standard deviation. It's biased because we only have sample data. But as long as we're aware that it's biased, that's all that really matters. Moving on. All right, so we're going to find the standard deviation. We could use this formula. When I first started teaching statistics, I did use the formula. Now I'm going to show you how to do this with a calculator. Now, I've already put the data into list 1 and list 2, so that's this data here. And so what you'll need to do is maybe pause the video so that you can put your data in. And here's how this works. I'm going to go to Stat and Calculate. This is our first use of one variable statistics. One var stats. And once again, let me show you how to get there. So you hit Stat and go to Calculate. It's the first thing, one variable stats. Now I put this into list 1, and there shouldn't be anything with the frequency list. So I'm going to find the standard deviation for this here. And remember to find L1 and L2. It's above my 1, my 2, my 3, my 4, 5, 6, and so on for the various lists. And what I mean by that is, if this wasn't list 1, then I could change it to be list 1. There it is. Then I calculate. This gives me the mean, 23.4. The standard deviation for a sample is going to be the S. So in this case, S is about 1.6733. I'm going to run the same thing on the other list. So quit out of that. stat calculate one variable statistics. And I'm going to change that to list 2, second 2 is my list 2, and then calculate. So it's nice it does this for us. So S is about, in this case, 1.6421. And we have what's called the range rule of thumb for identifying significant values. And that is going to look like this. So we have the minimum usual value is going to be the mean minus 2 standard deviations. And the maximum usual is X bar plus 2 standard deviations. So anything more than 2 standard deviations away from the mean is considered unusual. Now, we're not talking about unusual people or anything like that. It just means that whatever the data values are that are outside of 2 standard deviations is unusual. And we'll come back to that later in the semester as to why 2. All right, we have example 8. The mean is 24 chocolate chips, and the standard deviation is 2.6 chocolate chips. Use the range rule of thumb to find the minimum and maximum usual number of chips. This is on a chocolate chip cookie. So the minimum is going to be the mean, 24, minus 2 times the standard deviation, which is 2.6. 24 minus 2 times 2.6, 18.8. We'll just say about 19. The max is going to be 24 plus 2 times the standard deviation, 2.6. 24 plus 2 times 2.6. So we'll say 30. 30. So any given chocolate chip cookie in this batch, it'll have anywhere from 19 to 30 chocolate chips on it, and anything more than 30 chocolate chips is going to be unusual. Anything less than 19 is unusual. Now you'll notice this wasn't quite 30, and it's asking if 30 chips are unusual, so we're going to say yes. In fact, I'll specifically put 29.2, which is less than 30. So it's unusual. Next up, we have the range rule of thumb for estimating the standard deviation. And that is going to be the range that we learned earlier in this video, the max minus the min divided by 4. And I'll talk more about why 4 here in just a few minutes. So use the range rule of thumb to estimate the standard deviation of the sample with a minimum of 19 and a maximum of 30, kind of what we did up here. Well, that means the standard deviation is going to be about 30 minus 19 divided by 4. 30 minus 19 divided by 4. So 2.75. And we know from the previous problem that the standard deviation was 2.6. So it's not too far off. Again, this is only if you have to use that. We, of course, would always want to calculate it. We have some notation we want to clear up. The sample standard deviation is a capital S. The sample variance is S squared. Population standard deviation is a Greek letter sigma. The population variance is the Greek letter sigma squared. So its population usually has the Greek letters with them, just like the mean with the mu and the X bar and so on. And here is the empirical rule for data with a bell-shaped distribution. Now, I want to point out that if we go 2 standard deviations out, the area under this curve, which we'll talk a lot more about when we get to a different chapter, makes up 95% of all of the data is going to be within 2 standard deviations away. So that's the reason that we have 2 standard deviations. Now, I told you, why are we dividing by 4 on that previous formula? Well, you can see there's 1, 2, 3, 4 parts there. That's where the 4 comes from. So if I go 1 standard deviation out, I have 68% of all the data is going to be there. 2 out is 95%. 3 out is 99.7%. We usually don't go 3 out. That's unusual. All right. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentages of IQ scores are between 70 and 130? So I want to point out that if the mean is 100, if I go 1 standard deviation away, which is 15, that's going to be 115. And that is going to be 85. If I go 1 more out, 130 and 70. So this is telling us that we are going 2 standard deviations out. Two standard deviations out, if we use the empirical rule, we can see that that gives us 95%. And lastly, we have Chebychev's theorem. This is in case we have a distribution that is not normally shaped. So it's not shaped with the bell curve. Then we have another way to estimate the standard deviation. The proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 over k squared. So if k equals 2, that means 75% of the data is within 2 standard deviations away. If k is 3, you can see the math here, then 89% of the data is contained, at least 89% of the data is contained. So that brings us full round here. IQ scores have a mean of 100, standard deviation of 15. What can we conclude from Chebychev's theorem? We can conclude that 2 standard deviations away from the mean will give us 75% of the data. And 3 standard deviations away will give us 89% of the data. There you go.